All right, in this lesson, we're going to talk about how to find the measures of segments in circles, and we're going to go over 3 different theorems or rules, and then how to use Pythagorean theorem to solve for missing segments in circles. So something I should differentiate between what we're doing today and what we did previously is before we've been only talking about angles and arcs. Well, in this lesson, we're now going to be talking about lengths of chords and tangents, etc. So we're no longer thinking about arc, the measure of the arc or the measure of any angle. We're now just thinking about how to find the measures of line segments, how long certain segments are in circles. All right, so the first rule or theorem we're going to talk about is called the chord radius rule. And the chord radius rule states that if the radius, which is EA in this picture, is perpendicular to a chord, which is BD in this picture, then it means the radius is a bisector. Okay, so what that means is this. First of all, perpendicular. To remind you, perpendicular means that it crosses at a 90-degree angle, so it means that this angle is 90 degrees. And when we say that something bisects, this means to cut in half. Okay, so again, it says that the radius, if it's perpendicular to the chord, then the radius cuts the chord in half, which tells me that BC and CD are the same length. Okay, so putting this in symbols, it's basically saying if EA, which is the radius, is perpendicular to BD, which is the chord, then this is what's true. BC is equal or congruent to CD. Okay, for all of these examples, we're going to be looking for right triangles, okay, because we can then use Pythagorean theorem to solve for right triangles. So in looking at this, since we know that the chord and the radius are perpendicular, if this angle right here is 90 degrees, it also means that this angle right here is also 90 degrees. So the right triangle we're looking at is this one right here. So let's look at an example problem to see how we might apply this. Okay, so looking on the inside here, let's look at this first example. Okay, we're trying to find the measure of BD. Okay, so BD is this length right here. And what we are given is we are given that the radius, which is EA, is perpendicular to our chord, which is BD. I'm going to actually have it in blue. Okay, so in this problem, like I said, we're going to look for our right triangle, and our right triangle is going to be here. Okay, so here's what we know about our right triangle. We know that this side length is 2, so what I'm actually going to do is I'm going to redraw my right triangle. I know that this side is 2. I know that in my original diagram, this segment and this segment are congruent because of the chord radius rule. Okay, so that means if I could solve for this segment, I could just double that to get the length of BD. So this is a segment I'm solving for, so I'm just going to call that X. Okay, the question is, what is this side, which is our hypotenuse? Well, if you look at your circle, the hypotenuse of this right triangle is really just the radius of the circle. And remember that no matter where you draw the radius, it's the same length in the circle. Well, there's a radius here too, and we know that this is 4 and this is 2, which means my radius is 4 plus 2, which is 6. So the hypotenuse of my right triangle is 6. Now I can use Pythagorean theorem to solve for my third side. So using Pythagorean theorem, it's going to be 2 squared plus x squared equals 6 squared. So 2 squared is 4. Then we have x squared, and then we have 6 squared, which is 36. So now to finish solving, we subtract 4 from both sides. So x squared is equal to 32. And then we take the square root of both sides. So x is about 5.66. Okay, so 5.66 is this part right here. But because of the chord radius rule, we know that this side right here is also 5.66. So for these types of problems, I do want you to explain. So I'm going to write down an explanation for this. So by the chord radius rule, the radius bisects the chord. So the length of the chord BD is 5.66 times 2, which is 11.32. And there's my answer. So to go back over it one more time, okay, what we were given is that our radius is perpendicular to my chord, okay, which we could then form a right triangle. The hypotenuse of my right triangle is the radius of my circle, and the radius of my circle is 4 plus 2, which is 6, which is why we knew that our hypotenuse was 6. I knew that this part of my right triangle was 2, so using Pythagorean theorem, a squared plus b squared equals c squared. We had 2 squared plus x squared equals 6 squared. And then when we solved for x, we got 5.66. Well, 5.66 represented half of my chord, because by the chord radius rule, we know that our radius bisects the chord if it is perpendicular. So to solve for the full length of BD, I just take 5.66 and multiply it by 2. All right, let's look at one more example. Okay, similar example here. So in the diagram below, we know that QR is perpendicular to PS. Perpendicular means it crosses at a 90-degree angle. We want to find the length of QR. So QR is my chord, and I know that my radius bisects it. So just like the previous problem, we're going to go ahead and draw in our right triangle. And it doesn't really matter which side you draw it in. Okay, so using my right triangle, I'm going to redraw it right here. I'm going to fill in what I know. Here's my right angle. This side up here is 5. I'm solving for this side because remember, once we have this side, we just have to double it to get the length of QR. The hypotenuse is my radius, okay? So in looking at our radius, the information that we're given here, the red line is also our radius, so that's 5 plus 4. So my hypotenuse is going to be 5 plus 4, which is 9. So my hypotenuse of my right triangle is 9. So now I could use Pythagorean theorem to solve for x. 5 squared plus x squared is equal to 9 squared. Always make sure that your hypotenuse is by itself. So 5 squared is 25 plus x squared is equal to 9 squared, which is 81. We're going to subtract 25 from both sides. 56, and then we're going to take the square root. So you get x is about 7.48. So again, to write my final answer, I'm going to explain. So by the chord radius rule, the radius bisects the chord. So the length of the chord QR is equal to 7.48 times 2. So QR is 14.96. And there's my answer. So I know we're not used to really writing explanations like we're writing here, but because you are using a rule or a theorem, you do need to state the theorem that you are using. You can't just multiply by 2, you have to be able to explain why you are multiplying by 2. All right, now let's look at the second theorem here. So the second theorem is called the tangent to a circle theorem, and it states that a line drawn tangent to a circle, so it's this one, is perpendicular, which we know means crosses at a 90-degree angle, to the radius of the circle when it is drawn to the point of tangency. Okay, so it's basically just saying, I mean, really, this is really just an inscribed angle if we think about it. The vertex of this angle is on the circle, okay, and the arc for the angle is 180 degrees, which is why this is a 90-degree angle. So in this problem, again, for all of these, we're looking for a right triangle. So if we connect these points, here is our right triangle. Okay, knowing that this is a 90-degree angle allows us to use Pythagorean theorem. All right, so now let's take a look at a couple examples. Okay, so for this first example, we're solving for x, which is right here. So that line is tangent to the circle, which means that this is a right angle. So I'm going to start off by saying, since there is a tangent line drawn to the radius, the triangle is a right triangle. By the tangent to a circle theorem. Okay, so now we can use Pythagorean theorem. So since I know that that is a right triangle, I'm going to use Pythagorean theorem. So first of all, it might be helpful to redraw your right triangle here. Okay, so this bottom part right here is 7 inches, and that's the radius of my circle. Here's my right angle. Okay, we have to be careful because 4 does not represent this whole entire length. If 4 represented this whole length, this would be more towards the middle. This length right here is 4. So this part, remember, this is just the radius of the circle, so this part is also 7, since the radius is 7. Which tells me that this entire side, or the hypotenuse of my right triangle, is just 7 plus 4, which is 11 inches. So the hypotenuse of my right triangle is 11 inches. So now I could solve for x using Pythagorean theorem. So Pythagorean theorem, a squared plus b squared equals c squared. So 7 squared plus x squared equals 11 squared. So 7 squared is 49. X squared, and then 11 squared is 121. So now I'm going to subtract 49 from both sides. So I have x squared equals 72. And then we're going to take the square root of both sides. So 8.49, about 8.49. So in terms of my answer, I do want a little bit of an explanation here to show that it is a right triangle, and then you can just show the work to have the final answer here. All right, let's take another look at another example. So this is pretty similar. So I'm not going to rewrite my explanation since I wrote it already in example 1, and just to make things go a little bit more quick, because it's going to be the same exact explanation. Whenever you have a line drawn to the radius, a tangent line drawn to the radius, it forms a right angle, which means this is a right triangle. Okay, so using what we did in the previous problem, again, I have my right triangle here based on the tangent to a circle theorem. I have my right triangle. I'm just going to redraw it here. This is 15. This is x, and remember, this part right here is also 15, since my radius is 15. So the entire length of this hypotenuse is 15 plus 7, which is 22 centimeters. Okay, so now that I have my right triangle, I'm going to use Pythagorean theorem. So a squared plus b squared equals c squared. So x squared plus 225 equals 22 squared, which is 484. And now we're going to subtract 225 from both sides. So x squared equals 259. And last step, we're going to take the square root of both sides. Which is about 16.09, which is our answer. All right, let's take a look at the another theorem. So the theorem states that if two segments are tangent from the same point, then they are congruent. Okay, so if two segments are tangent from the same point, so here are my tangent segments, and here is the point that they are tangent from, it tells me that they are congruent, which means they are equal. So in this case, BA is congruent to CA. Okay, so let's see how we can use this. Okay, it's fairly straightforward. So here it says DE and DF are tangent to circle C. Find the length of DF. So since these 2 points are tangent from the same point, so I'm going to write my explanation point first. So since DE and DF are tangent from the same point, by the tangent segments theorem, they are congruent. Okay, so that means we can set them equal to each other. So basically we would just do 2x plus 7 equals 3x plus 2. Okay, so solving here, remember when you have variables on both sides, you can just choose whichever variable you want to move first. So I'm going to start by subtracting 2x from both sides. So on this side I have 7, so 3x minus 2x is x, and then I have plus 2, and now I'm going to subtract 2 from both sides. So 5 equals x. So we're not done because the question's asking us to find the length of DF. So DF is this segment here, so we're just going to plug it in. So 3 times 5 plus 2. So we're just taking the answer we found and plugging it in for x right there. So 3 times 5 is 15 plus 2, so DF equals 17. All right, let's look at the second example. So again, I'm not going to write my explanation twice just because I already wrote it, so you don't have to write it again. We're just going to apply the tangent segments theorem. So tangent segments theorem states that when we have two lines tangent from the same point, those two lines are congruent, which means we can set them equal to each other. So 4x plus 14 equals 5x plus 6, and then we're just going to solve for x. So I'm going to start by subtracting 4x from both sides. So then I have 14 equals x plus 6, and now I'm going to subtract 6 from both sides. 14 minus 6 is 8. So in this case, we don't need to plug it back in because the question was just saying to solve for x. So once we solve for x, we're done. All right, my last piece of notes here is just kind of re-emphasizing the fact that we can use Pythagorean theorem and our circle theorems to solve for missing segments. So in each case, these were kind of the three cases we looked at, you can form a right triangle. So in this first case, which is the one that we just talked about, it's kind of applying two theorems. The first theorem is the tangent to a circle theorem that states that every line drawn tangent to a circle to the point of tangency is perpendicular, which means we can form a right triangle there. The second one here, if we just connect these points, this is a tangent to a circle theorem that forms a right triangle here. And this third example, when a radius is perpendicular to a chord, you can form a right triangle right here. So in all these cases, because we have a right triangle, we can use Pythagorean theorem. So let's just see one more example here. So this is applying a couple theorems. So it's applying the theorem that we just talked about, which is the tangent segments theorem that states when two lines are tangent from the same point, we know that these lines are congruent. And we're also going to use the tangent segments theorem that states that when we have a line drawn tangent to a circle, it is perpendicular to the radius, which forms a right triangle here. Okay, so first thing we're going to do, and I'm going to write out the step-by-step directions here. Step one is we're going to solve for x using the tangent segments theorem. Okay, so we're going to set these equal to each other, so 2x minus 5 equals x plus 2, and we're going to solve for x. So I'm going to start by subtracting x from both sides. So 2x minus x is x. These x's cancel out, and then I'm going to add 5 to both sides. So x equals 7. Okay, so step 2 is we're going to plug in x equals 7 everywhere we see it, basically. So we solve for x, we get x equals 7. Now I'm going to plug it in everywhere I see an x. Okay, so we are going to take this top triangle here, and we are going to use that to solve for DF. Oops, this is a typo actually. This should say solve for DC. So make sure you fix that there, that we're solving for DC, which is the hypotenuse of that triangle. Okay, so plugging in x equals 7, this is 2 times 7 minus 5. So that's 14 minus 5, which is 9. So this line segment's 9, which we know that this one is also 9. And then I'm just going to plug in x here. So this, since x equals 7, the radius of my circle is 7. Okay, the last step, step 3, is we're going to use Pythagorean theorem to solve for missing length. Okay, so I'm going to take my right triangle that I drew here, and I'm going to redraw it over here. So here's my right triangle, and I'm going to fill in the measurements I know. Okay, to the tangent to the circle theorem, I know this is a right triangle. I know that this is 9 and this is 7, and I'm solving for DC, which is my hypotenuse. So I'm going to call that x. All right, now this just becomes a pretty straightforward Pythagorean theorem problem. A squared plus b squared equals c squared. So 9 squared plus 7 squared equals x squared. 9 squared is 81. 7 squared is 49. It's x squared. So now we're going to add these together. So 81 plus 49 is 130. And now we're going to square root both sides. So that's 11.40. So that means DC is 11.40. Okay, so this problem is using two of the theorems, like I said, the tangent segments theorem, which states that these segments are equal, so we use that to solve for x. Once you have x, we're going to use the tangent to a circle theorem that makes this a right triangle in order to solve for DC, which is the hypotenuse of that right triangle.